Assalamu alaikum. In continuation of our previous lecture, today's topic is FSK, frequency shift keying. Previously we have presented BPSK and ASK modulation scheme, right? These two. Now today's topic is frequency shift keying. FSK. So this is another modulation scheme in digital communication. Now, unlike previously in both BPSK and ASK modulation, we used only one pulse. So this time we need actually two pulse. So our pulse would be P1 and P2, for example. So pulse P1 can be expressed as like previous condition that, and P2 is expressed as this. Okay, so the two pulse will be distinguished by their frequency F1 and F2. Here we can define F1 is same as previously, K1 by T. T is the symbol duration, and F2 is K2 T, where K1 is not equal to K2. Here both K1 and K, like previously, previous BPSK and ASK, the K1 and K2 both are integer number. So also we can find, or we can find that F1 is R1 by, so T. So instead of F1 we can write T. T1 is nothing but 1 by so T T, yes, both T, not 1 T. For T is nothing but K1 by F1 equal to K2 by F2. That we also find from here, right? Okay, now what is the energy? The energy EP is nothing but the same thing as we did before, minus infinity to plus infinity, P1 square pt dt, or minus infinity to plus infinity, P2 square t dt, right? From previous case, we already find that their value is unity, right? So it's actually normalized to normalized unit energy. That's why it's marked as EP. So both have. So we can say, like previous our cases, as BPSK and ASK, both have unit energy. So also the inner product of these two, P1 and P2, minus infinity to plus infinity, also not also, so Also, so this is one condition. The other condition is also the P1 T and P2 T dt is 0. We say they are orthogonal. Because they are orthogonal, we have seen our orthogonality condition previously, right? When we have probably chapter 2. Because they are orthogonal and also their normalized energy is unity. So normalized energy is unity, or normalized unit energy unit. That's why they can be termed as orthonormal. So they are also called orthonormal. So this condition is also an orthonormal condition. Or this pulse P1 and P1 and P2, they are orthonormal pulse. Okay. Actually, P1 and P2 both are orthogonal. Remember what we mean by orthogonal? It is actually like this P1 and P2 pulse. For example, this is P1 and this is P2. They actually have 90-degree to each other. That's why they create orthogonal. You have seen it in earlier cases, right? Okay, so for information 0 and 1, we will see. So for information 0, what could be the pulse? A P1 T. Okay, which is actually our signal when we express as a xt, or when 1, then its signal can be A P2 T. Right? We have seen it earlier. These conditions actually are very familiar to us as previous. Because of this normalized unit energy, the energy will be A. The energy, we actually seen how we convert the expression for 0 and 1 for both previous cases. So okay, so this will be expressed as xt. The xt can be expressed as for both pulse P1 and P2. Okay, so if this is the case, then we can write it a little bit different actually. Yeah, we can write it a little bit different. Now, okay, it's okay. Xt. I can write it again. So xt signal have two options, right? For 0 and 1. So a P1T or a P2T, which can be written as actually a by T cos 2s by F1 T or a by T. This is for bit 0 and this is for bit 1, right? In both cases, here you see how the waveform differs. The waveform only differs by this frequency. That's why actually this scheme is termed as FSK, right? Frequency shifting. Individual bit will be differ in frequency. That's why this is a FSK modulation scheme, right? Okay. So, like previously, we assume so we assume assume both 0 and 1 bit have equal probability, or have probability T half, right? What is the average energy then? So the average energy, same thing, we also did it earlier, half f square EP plus half f square EP means actually f square EP. Okay, so we know EP is 1, so it's actually s square, right? So s square is nothing but the EB, energy per bit. So we can actually write that A is nothing but, it's the same thing as we did earlier, right? Because we already did the scheme for ASK, BPSK and ASK. So these few things will be repeating again and again. Eh? So for xt, we can rewrite the signal xt as this one. We are rewriting this one again by substituting EB. So the signal can be square root twice EB, right? Okay, so twice EB by T cos 2 pi f1 T. You see, we just replacing this one, or it can be twice EB by T cos twice pi f2 T. So this is for if the bit is 0 and if the bit is 1, 0 bit and 1 bit. Okay, now these are the signals. So these are the signals we transmitted. So what happens in the receiver? So in the receiver, you see the procedure is the same. We did the same procedure again and again. So in the receiver, remember how our receiver looks like? I have drawn it like several times, right? Many times. So our signal, let me draw it again. So you will, like, since the beginning of our lecture in so since the beginning of this lecture, we are actually drawing this as a digital communication receiver. Okay, so our signal was xt, signal goes, the signal got corrupted in the channel with a noise in T. The output of the channel becomes yt. Then this signal goes to the receiver filter having a response ht, assuming that this is a linear LTI system. Then the receive signal is rt. This signal will be sampled at t. The signal is sampled at t, so this becomes rt. So here actually we detect the signal detection, right? Detection. This is very, like, since our communication courses we have, so this is a sampler. So we have drawn this schematic several times. So here yt is nothing but xt plus nt. That's actually our receive signal. Okay, so yt is actually our xt plus nt. That we know is very famous scenario. Now here this is what? This is a AWGN, additive wide Gaussian noise, which have a noise power n0 by 2, right? Okay, we have derived this noise several times in our lecture AWGN. Okay, now for 0 or 0 bit, what output is yt equal to x. So x changes now, whether it could be p1 or p2 pulse. So a1 a p1t plus this noise, or if it's 1, then this output yt becomes a p2t plus n, right? Here there are two pulses. This scenario is totally different. The received signal is totally different compared to our previous scheme, right? In our previous scheme there was only one pulses. So here we have two pulse, two pulse, p1 and p2. Now because we are talking about the receiver, how would we have maximized our SNR previously? By using a mesh filter. When we did that in previous cases, we only had a one pulse, right? So the match filter is actually should be the similar to the this pulse shaping filter previously, because we had only one pulse. Now we had actually two pulse. So there will be a dilemma right now. So for our mesh filter, response ht, previously it was ht was what? When we have single pulse, p t minus tau, means actually the match filter response of the match filter is actually should be equal to the pulse shaping filter, so that the signal to noise ratio become maximized, right? But here we have two pulse. We have p1 t minus tau, or we have p2 t minus tau. So which one should be now? That's the question. To maximize, the condition is the same. We have to maximize the signal to noise ratio. But which condition should be? Now we have two distinct pulse. Okay. For that, we have to find it. Okay. To simplify this, what we did, let's say yt, this signal, let's subtract this amount from yt. This is a constant signal. This amount is a constant. And let's give it a name, y tilde. Okay. Instead of y, we have a new signal y tilde, and we subtract a constant amount from this yt. We can always do that. There is no difficulties on dealing with constant, because this is not a variable stuff, right? So for bit 0, so for bit 0, what we can write yt. So what's the for bit 0, yt equal to a p1t, that's actually the y value. If this is the case, then what is the y tilde value? Y tilde value becomes becomes a y tilde value is nothing but y t minus p2t divided by 2, isn't it? So that's actually, if this is the case, we assume this previously, right? So this actually I'm writing it this. So what we find? So we find the value will be a, so yt is already this value, so subtract this from here. We will have a p1t minus p2t plus this value in t. Okay, now let's give it a name to this one, p tilde. So the expression becomes, new expression becomes a p tilde t plus n t. Okay, this is our y tilde t. So we have a new expression for bit 0, which is this one. Okay, for bit 1, same thing, right? For bit 1, we know again yt is nothing but a p2 t plus n2. Sorry. Okay. Again, we do the same process. Okay, so y tilde t will be yt minus yt minus a p1t plus p2t. This new equation becomes right. Ah, little bit mistake here. Should be so p2 p1 actually. So our new expression becomes minus a. So let's give it the same thing like previously, p tilde t. So a, the expression becomes tilde t plus n t. Okay, let's summarize it. What we find. Okay, so for y tilde, the new value of output y tilde, we get two value. We get a p tilde t plus n t, or we get a p tilde t plus n. Okay, this is one for, this is for bit 0, and this is for bit 1. You see, this is very similar expression of what? Similar expression of BPSK, binary phase shifting, right? In BPSK, this notation was different. You see, here is negative and here is positive. So as if it's a looks like a BPSK. Okay, but only P is changes, right? So this is similar to similar expression of BPSK. And how it's similar to BPSK? Only PT is replaced by PT is PT replaced by E tilde. Where P, we know P tilde T is this expression, P1 T minus P2 T by half. This is the same expression of the BPSK, except the P in BPSK, this was P, and now we have P tilde, which actually in combination of a P1 and P2. Okay, so now we go back to our previous question. We can actually find this solution. Previously, our HT, we had the dilemma that HT, how the filter respond, whether it should be equal to P1, whether it should be equal to P2, because we do not know. Because so far we had the experience that filter response should be equal to the pulse response, while we had a single pulse. Now we had a two type of pulse or two pulse, P1 and P2 distinct pulse, but which one should be equal, right? But now we actually get rid of P1 and P2 by having a new expression P tilde. Though P tilde is a combination of P1 and P2, but we can have a single expression. So now we can actually uh, actually have the new expression for the match filter. Okay, so now the optimum match filter is for maximize SNR. So the optimum or optimal match filter is same expression, right, that we used previously. H T is, you see, for a single pulse. For a single pulse, what was the for maximum SNR? The optimal response should be Ht equal to P T minus tau, right? But for our cases, we converted P is to the P tilde. That's all. Okay, you see how we tricked so that we still can have a single expression. Here we can write it P tilde is nothing but combination of P1 and P2. So P tilde is nothing but a combination of P1T minus P2T divided by 2. Here half is the scaling factor, nothing else. Scaling factor, right? And which will not affect to the SNR, and will not affect SNR. This is just a scaling factor, right? So we can actually discard this half for while we having the expression, right? So we can write HT equal to P1 T minus tau. We are replacing with this signal, minus P2 T minus tau, right? The half is not coming here because this is a scaling factor and we can avoid that. So H T. So this is an optimal match filter condition. Okay. So if this is the optimal match filter condition, we can actually, or you can actually replace it with the pulse. P1 is nothing but 2 by T cos 2 pi F1 T minus tau minus cos 2 pi F2 T minus tau. So this is also the same expression that for maximum SNR. For maximum SNR, this is optimized match filter to get the maximum SNR. Now to find, because we already find the maximum SNR, we need to find the decision rule, or and also the beta error rate. Okay. For maximum SNR, we know this is the condition. Okay. So what will be the output? What will be the output YT? Because you see, we tricked a little bit. Now, so if we go back, you see, we are so far we are dealing with these Y tilde T. Now let's see what is the output YT, actual output YT. Okay, so consider for bit 0. Okay, we always have this combination for bit 0. Okay, so for bit 0, YT is A P1T, right, plus NT. We already know that. Okay, we already have the match filter. So what should be the receive signal? So receive signal RT is, so this is the receive signal. Oh, this is the receive signal YT, but we will sample it, right? So okay, so sampling at T equal to T at the sampler, eh? This happens here. Here. So RT you can find minus infinity to infinity Y tau H T minus tau D tau. Okay, so the receive signal, it should be the capital, because this is sampled at small t equal to capital T. Okay, so this is for information 0. Okay, we can have the receive signal where the YT have the YT goes through this YT signal actually pass through the, let's go to our, you see this YT pass through the filter response in the receiver, then we received it. So RT is a RT is nothing but YT with a complex conjugate with HT, right? Filter response. That's actually we are trying to write it here. So that actually we write it here. Okay. So we will replace these values. Let's say minus infinity to plus infinity. So we know y tau should be by changing the tau. So a p1 tau plus n tau is our y into this one h t minus tau. So if h t is this one, what should be h t minus tau? So we can have p1. You see, if h t is this equation, h t is this equation, what happens? 2h t minus tau. So both tt, this t and that t will be cancelled. So we will have a tau. We have a tau factor. So we will have p tau minus p2 tau. Actually, this is multiplied d tau. Okay, so we can rewrite this equation as minus infinity to infinity a p1 tau with this one p1 tau minus p2 tau d tau plus in this one again n tau with p1 tau minus beta d tau. Here we have two components. So this one, this is actually our signal component. Signal component, and this one is the noise component. Okay, so let's analyze them individually. Okay, signal component. So let me write the signal. So the signal component is like we are writing this one, minus infinity to plus infinity a p1 tau. So p1 tau minus pt tau d tau. So again we are writing it or separating it a minus infinity to plus infinity. So p1 and p1, so p1 square tau minus a minus infinity infinity p1 tau p2 tau d tau. Oh, I missed d tau here also. See this one, remember p1 and p2 is their product. So inner product of p1 and p2, we have seen it earlier, right? The inner product, this part is inner product, inner product of p1 and p2 should be 0. So this is actually 0, and p1 square, but p1 tau, p1 is unit. We say that they are orthonormal. P1 and P2 means actually their inner product is 0 because they are orthogonal, and their normalized power is unity. So this amount is unity. So this will be 1, right? Which is called EP, right? We know EP equal to 1, the energy. So we can write A E P, or actually it's actually A, which is actually our signal component. So signal component, this amount becomes 1. So let's see what happens to this noise component. Okay, so the noise component, now give it a name, in tilde. Noise component is minus infinity to plus infinity in tau p1 tau minus data. Okay, that was actually our noise component, right? So in this noise component here, this noise is, we actually deal with this earlier. This is actually Gaussian. That's why this will also be a Gaussian. Gaussian with mean 0. Mean 0. We don't know the variance, but at least we know the mean. So what should be the variance? The variance of this signal is nothing but n0 by 2 minus infinity to plus infinity. We can have this response of this signal h t minus tau, t minus tau d tau should be the square. Okay, so this can be written as n0 by 2 minus infinity to plus infinity, replacing h with p1 tau minus p2 tau square data. It's nothing but n0 by 2 minus infinity to plus infinity. This square should be p1 square tau plus p2 square tau minus 2 p1 p2 data. Okay, so here we can see this is again the inner product. So let's write it separately. Okay, let's write it separately. So okay, this is inner product. This will obviously will come to 0. Okay, let's write it separately. It will be easier for us to understand. P1 square tau plus okay, yeah, and 0 by 2 minus infinity to plus infinity minus plus 0 by 2 minus infinity to plus infinity. So 2, this 2 can be outside. So P1 tau P2 tau, d tau should be everywhere. So d tau should be everywhere, d tau. Okay, this is 0 because of this inner product. So we can write this is n0 by 2. Okay, this is again equal to EP equal to, so this is equal to EP equal to 1. This will also be EP equal to 1. So n0 plus 2 by n0 plus 2 equal to n0. So the variance actually n0. So we know this is a Gaussian uh, distribution with a mean 0 and variance n0. The new our noise power after sampling. So this is the noise power after sampling. The variance. So the variance, this is noise power after sampling. Here, here after sampling, here the noise. So this noise in T, because they pass through the filter, here I gave it a new name, n tilde T. So this noise has a mean 0 with a variance n0. Okay. Okay. So let us write the RT is a RT is nothing but the combination of the two signal. Where we write it? Okay, so this RT having two signal, having like two component. One is a signal component and as a noise component. Okay, so we individually derive the signal component, which is actually this one, and we also derive the noise component, which is actually here. So let's write it. So A plus noise component and tilde, where this noise has mean 0 and variance n0. Okay, so we can do the same thing for bit 1. So for bit 1 yt, like if I repeat the previous steps, for yt will be, so I'm repeating this step again, so we will not go through all detail. So y3 equal to a p2t plus n, that was y2. We follow the same procedure of the match filter. So our RT, we can directly write the RT signal will be minus a plus n tilde, like this equation. Okay, so we have two equation. One is this one for bit 0, and we have equation for this one. Same condition. For this n2 also have the mean 0 and variance n0. Okay, so we can write it nicely that RT, yeah, we can write that RT have actually two values. One is a plus n tilde and minus a plus n tilde for 0 and 1. Now you see this one, this is a decision rule RT. Let me write it nicely. So this is our decision rule for FSK, which is actually looks similar. This is also similar to BPSK, except our variance is actually n0 here. Okay, the decision rule. This is actually our decision rule for. So, if what you can have optimum decision rule from here, we can find it if RT, or we can rewrite it a little bit different. RT is greater than 0 then we had decided A0 was 0, right? And RT less than not equal to less than 0, we decide A0 equal to 1. So optimum decision rule is found for so this is actually our decision rule. So this is actually our optimal decision rule. Okay, so we decision rule for FSK. So we know the optimal decision rule, but need to find it more. So we have the transmission signal, we find the optimal decision rule. What else? Bit error rate. So let's find the bit error rate. Let's find the bit error rate for FSK. So bit error rate will be nothing but the Q factor A by sigma, which is actually Q of our A power is A, sigma is N0, right? So we can write Q equal to nothing but A square by N0. What do you have? N square. We can replace this. A square equal to Q EB. A square is nothing but, so EB by N0. So this is the bit error rate for FSK. So bit error rate for FSK. Is this bit error rate look similar? Yeah, it looks similar. What is the bit error rate for BPSK? BPSK, it was Q twice EB by N0. For bit error rate ASK, what was the expression? Q by EB by N0 means bit error rate of FSK has the similar nature of the bit errors of bit error of FSK similar to the bit error of ASK. So if we compare, we also compare it for ASK and BPSK. We made this comparison, right? So we can easily write that bit error rate for ASK, which is actually similar to bit error rate of FSK, which is actually higher than bit error rate of BPSK, right? So the bit error rate of BPSK has 3 dB more, what is called the 3 dB more power, right? So for same bit error rate, ASK and FSK need 3 dB more power than the BPSK. So this was the same, because this was the conclusion for what is the conclusion for ASK is the same conclusion for FSK also. So the conclusion is we have seen it in our ASK solution, right? For same bit error rate, ASK or FSK, which have the same bit error rate, need 3 dB more power. Or opposite, BPSK need half of the bit energy rate. Bit energy per bit. This is actually the conclusion. So we can conclude that BPSK is still better than. Previously, our conclusion was BPSK is better than BPSK. So for same bit rate, FSK need 3 dB more power than BPSK. We previously concluded that BPSK is better than ASK. Now we find that the bit rate of ASK and FSK is similar. That's why the performance of BTSK is better than FSK. That's actually our conclusion. So we will stop here. Assalamu alaikum.